Hey, what's up, YouTube fans? So the topic for this video, right, is how there are levels of homology, right, differing levels of it, right? So a homologous structure, right, is a structure shared between different species that is inherited from a common ancestor, right? And there are differing levels of homology, right? Because so for example, the chimpanzee arm and hand, right, is homologous to the human arm and hand, right? And but then also the dog front legs and feet are homologous to the human arm and hand, right? But not as much so, right? Because there's some modifications that happen to these limbs in the ancestors of both chimps and humans that happened since we split off from our last common ancestor with dogs, right? And so while some of the fundamental parts are already there in the dog, right? Not all of them, right? So that's another level of homology, right? The extent to which other mammals share the same limb structure, the extent to where most tetrapods share the same limb structure, right? All tetrapods that still have their limbs, right? But then there's even deeper levels of homology, right? Where sometimes the structure itself, right, between different groups will not be the same structure, right? And yet differing structures between different groups will share a common developmental and genetic origin, right? And so then at that level, there's a homology, right? Because the genetic instructions were evolved before the body part itself, right? The genetic instructions and developmental paths, much of them were evolved before the body part itself, right? Only later being put towards building that body part, right? And there's many identified examples, right? So like, for example, the malleus and incus bones, right? Unique to the middle ear of mammals, all mammals and only mammals have the malleus and incus bones in our middle ear. It's one of the many traits that all mammals have and only mammals have, right? They share a common developmental and genetic origin with the quadrate and articulate bones, which all of the mammals do not have, but most other jawed vertebrates do have, right? So much of the same genetic instructions as are used for building the quadrate and articulate bones, which mammals don't have, but most other jawed vertebrates have. Much of these same genetic instructions are used for building the malleus and incus bones, right? And we see embryologically, right, that these bones start out when they first form in mammals, they start out at positions more like the quadrate and articulate bones, right, more towards the jaw area. Only later into development, they migrate, they move, making their way into the middle ear, right? And in the case of marsupials, since marsupials, they are not in the womb for as long as placentals like me and you, right? Marsupials, for many of them, this change of the position of the malleus and incus bones doesn't happen until after they're already born, right? Within like a few weeks after they're born. So when they're first born, the malleus and incus bones are still down lower more by the jaw area. And then later into their development, it moves up into the middle ear, right? So the malleus and incus bones, they share a common developmental and genetic origin with the quadrant and articulate bones, right? And so that's an example of where, even though the body parts themselves are not the same structures, right? But genetically, right, at the genetic level, there's a homology, right? And so and this is the case for many of the body parts we have, right? That even in other groups that don't have it, they have some of the same genetic instructions for making it and some of the same developmental paths for making it, but in them it just ends up eventually developing into something different, right? And so therefore meaning that the genetic instructions did not have to be totally evolved anew from scratch when the body part that we now have was evolved, right? Because much of the genetic instructions were already in there and were just as good for building other structures, right? And with the malleus and incus bones and quadrant articulate bones, right, they come from pharyngeal arches, right, which form during embryonic development. And we see in fish, they also form pharyngeal arches during embryonic development. But in them, part of what it develops into is their gills, right? And so the same genetic instructions and developmental paths, right? Developmental paths such as developing pharyngeal arches, right? These can lead to very different structures, right? And so then the end structure between different groups is no longer a shared structure, it's different, and yet it's still at the developmental level, at the genetic level, at that level, you have a homology, right? And so there are differing levels of homology, right? And so just because a different group from humans, right, just because they don't share certain body parts that we have, right, that does not always mean that they do not have any of the genetic instructions for building those body parts, right? Oftentimes they still do, right? And they share much of the same developmental path that in us leads to the body part, right? But in them it builds something else, right? But much of the genetic instructions, the developmental paths are already there before the body part itself is evolved, right? And another good example, so humans and most other therian mammals, right, we have very different reproductive anatomy and setup of like our anus setup down there, right, compared to monotremes, reptiles, birds, and amphibians, right? Most of them have what's called a cloaca, right, which is a single multi-purpose hole, right, used for peeing, pooing, and laying eggs, all from one single hole, or if they're a male, releasing sperm from that hole, right? And during embryonic development, though, therian mammals, including humans, we actually start out having a cloaca, a single hole, right? But then what happens is later into development, it divides into separate holes, right? And so then that is how for us, we get the anus as a separate hole from our urogenital tract. And then also for females, that divides into two separate holes, urethra and vagina, right? And there's again a lot of the same genetic instructions used and the same beginning part of the developmental path, right? But then it deviates, right? And so, and then also what's interesting, right, is with the evolution of the gut tube to begin with, early on, the earliest digestive systems with a gut, the earliest ones likely had a single hole used both as mouth and anus. We still see this in jellyfish, flatworms, some creatures like that. They have a gut that it's called a gastrovascular cavity. It's a cavity open to the external environment, and there's a single hole which takes on both the role of mouth and anus, right? And but what's interesting, right, is that some evidence indicates that how the anus was first evolved, right, where we transitioned from that setup to having a gut tube with two ends, right, is that the gastrovascular cavity likely became linked up with a reproductive pore found in some invertebrates called a gonopore, right? And this is supported by the fact that there's some of the same genetic instructions that are used for making a gonopore are also used for making the anus, right? And so that, along with the fact that we also see that many vertebrate groups have a cloaca, right, where their reproductive hole and their poop hole are the same hole, right? This indicates, right, that likely the gastrovascular cavity, right, became linked up with the gonopore, right? And then that's how we had the transition then from gastrovascular cavity to a gut tube with two separate ends for eating and for pooping, rather than having to use a single hole for both of those purposes, right? Also worth noting is then those early steps where the gut was a gastrovascular cavity, there was no coelom. The coelom is the mesoderm-lined cavity between the gut and the outer body wall. We see in creatures like flatworms and jellyfish, they don't have a coelom, so their gut is directly fused to their outer body wall. There's no space in between, right? And so that comes later after the gut itself. Um, I talked about that in other videos, right? But so in any event, we often find, right, that very different body parts, right, which are structured very differently, right, much of their development in the early embryonic stages is the same, right, even though the end result is very different. Their development is much the same, and they share much of the same genetic instructions, right? And so, just because an animal does not have the same body part that we now have, right, does not mean that they do not have any of the genetic instructions for building the body part, right? And also, in some cases, they partially have the body part. Like in the case of dogs, they have forelimbs, right? Which have much of the same fundamental structure as our arms and hands, with humerus, radius, ulna, carpals, metacarpals, and digits with phalanges. But in them, it functions as legs and feet, so they don't have arms and hands, right? But they do have much of the same parts as the arms and hands have, right? And so there are differing levels of homology, right? All right, that's all for now. See you guys.